Hello, ladies and gentlemen. Today we're going to be discussing the kinematic equations, which are the equations that describe the motion of an object. Now, we've already looked at one equation before in the last video, which was the acceleration is equal to the change in velocity over time. What we're going to do to start off by making equations is we're going to be doing a combination of derivations, basically combining equations and rearranging them, but also we're going to be looking at graphs and see how we can get equations from those. Now, the important thing to note is when we're doing all these derivations, if you notice that the text is in a dark purple, that means you don't have to write it down. I'm not going to make you write all of these steps. They do get quite crazy eventually. So just sit along, kind of listen to it, and then once you see that black text appear, that's definitely something important to write down. So to start off with, we have the equation that we learned in the last video, and what we're going to be doing is we're going to be breaking it up and simplifying it, starting with that delta. What a delta means is a final minus an initial value. One big case you used it before is in chemistry with delta t. Now we're going to be using it with velocity. So the final velocity is the speed or the velocity at the end of the problem or the end of the situation or the end of the data taking, what have you. The initial velocity is whatever it is at the start, divided by the time. Now all I've done here is just multiplied both sides by t. And then I'm going to add both sides by, add vi to both sides. And then in just a simple rearrangement, we get that the final velocity is equal to acceleration times time plus vi. Now this is fundamentally the same equation as before. You can get the same information out of the a equals delta v over t as you can with the vf equals at plus vi. You can get the same information. It's just a little bit easier to use in most cases because you don't have to deal with the delta. Both of these equations are found on the reference table. The first equation being v equals d over t, the second one being this one up here, and then the third equation being this one right here. Now, to look at an actual new equation, we're going to be using our velocity versus time graphs to help us out. And we're going to be building a general equation for distance using these graphs. And if you remember, distance is the area under the curve. So we have a line here. It's the area underneath it is the distance of this graph. So we're going to be making a general equation for it. And that works for all cases where the velocity is constant, where the velocity is a straight line, either going upwards or straight line horizontal or straight line going down. And that is all the cases we're going to be doing in this class. We'll never have to deal with something where the acceleration is changing, where the velocity is curvy. We won't be seeing that. So this is a general formula for all velocities that are constant. So what I'm first going to do is I'm going to break up the area under the curve or the area under this line into two parts, this rectangle and this triangle. And we're going to find the area of both of these in a general case. So for this rectangle, we know that the area of a rectangle is base times height. The base of this triangle is whatever the time that elapsed, so time from 0 to whenever. The height of, that rectangle, the height of that rectangle is whatever speed it starts at. So from here to up here. So whatever the starting speed is the height of that triangle. I keep saying triangle, rectangle. Now, in a lot of cases, our initial velocity is going to be 0. We've already made quite a lot of these velocity versus time graphs where that's the case. However, sometimes it won't be 0, and this is the case for either or. You can plug in a 0 here or not, depending if it starts at 0 or not. Next, we're going to be looking at the triangle. The area of a triangle is 1/2 base times height. The base of this triangle is, again, time. And the height of this triangle is the final velocity, the speed it is at the very top, minus the initial velocity, the speed it is down here at the bottom. And that's going to be my overall height of the triangle. Now, what I'm going to do here to simplify this is I'm going to actually use our old equation back from the last slide. I'm going to replace this VF minus VI by AT because I know this relationship is true. We saw it on the last slide. So what I'm going to do is I'm going to replace this VF minus VI with AT and end up with distance is equal to 1/2 T times AT. So what we have here is we have the rectangle that has the formula of distance equals vi times t, and we have the triangle that has the formula 1/2 t times at. And what this is going to help us do is find the relationship between acceleration and distance if we need to solve it. Now, I call the equation that we're about to make when we sum these two together El Grande, because I call it the big one. It's the one that gives you, we're going to be using most. It gives you everything, pretty much everything you need to know about a problem. So the combination of these two, the sum of these two things is vi times t plus 1/2 t times at. And if we just want to simplify these times over here, and this is how it's written on the reference table, is that the distance is equal to vi times t plus 1/2 at squared. So right here, we find the relationship between acceleration and distance. And this formula right here, which I call El Grande, we're going to be using quite a lot. It works in a large variety of situations for dealing with the motion of an object. Let's give an example of that. Let's say that we have a speedboat that's accelerating uniformly from rest at a rate of 2.5 meters per second squared for 9 seconds. How far does the boat travel during the acceleration? And we talked about last video, the number one thing to do in a problem like this is to make the shopping list. So the shopping list is each individual variable and what they are. So to start off with, our acceleration, if we read the problem, is 2.5 meters per second squared. Our time is 9 seconds. Our initial velocity, though it doesn't state an initial velocity is this, where you gather it, and this is from the last video, is it starts from rest. So that initial velocity is 0. And finally, we're looking for the distance. How far does it go? So to do this, I'm going to write down our new equation, El Grande. I'm going to plug in all of the variables. So all I did was just take all the shopping list and plug it into each section. Once in a physics problem, you have the equation figured out that you want to use, and you have the shopping list done, the rest of it should be very straightforward math. So we have 0 meters per second, because that's our initial, times the 9 seconds plus 1/2 a 2.5 meters per second squared times 9 seconds squared. It is key that you put the units in here too. I know the first urge is to ignore the units and just put in the numbers. You have to put in the units. Because of that, this squared, make sure you put parentheses around here. I've seen this a lot where people forget the parentheses, and then I call it lose the squared in the unit. They see seconds squared and they forget that they have to square the 9. If you put the parentheses around it, you should remember that you're squaring the 9. This will go to 0 because it's multiplied by 0. That happens a lot. If our initial velocity is 0, it cancels out. And like I said, it's a pretty common case. So simplified, we have this over here. All I do, plug that in my calculator, and I get 101 meters. That's how these problems go. All right, next we're going to be looking at the VF squared formula. So this is a bit of a longer derivation where what we're going to be doing is we're going to be combining the two formulas we've already talked about into one big formula and then work to simplify it. There's a lot of small math tricks here, and it's not too key that you follow along exactly step by step. But what I want you to get out of this is that this equation doesn't just come from nowhere. This equation comes from the equations that we've already seen with the definition of acceleration is where this equation comes from. And then just by studying a velocity versus time graph, we see where this equation comes from. All we're going to be doing is combining the two. And our goal for this one is to get VF. If you'll notice, El Grande is missing final velocity. So if we had to find the final velocity in a problem, or if we were given the final velocity in a problem, El Grande would not be helpful to us. That's why we're using this equation. First thing I'm going to do is I'm going to solve for t here, which we actually saw this back in the relationship for what a general formula is. All I've done is subtract both sides by the initial velocity and divided by the acceleration. And I'm going to take this new formula and I'm going to plug in the times. And we end up with this massive formula when we do that. All I've done is every time where I see time is we plugged in VF minus VI divided by A. Now you can probably already notice the problem we're going to run in with. Not too much of a problem, but the larger math we're going to have to do is due to this squared over here. We're squaring this massive thing. When we do that, this is the same formula written again. When we do that square, we end up with this massive equation. What I'm going to do first is I'm just going to simplify this 1/2 A times the a squared and just make it 2a down here. So all I've done was just move this 1/2 a into this part of the equation. And I'm going to multiply both sides by 2a. And when I multiply both sides by 2a, we get 2a over here. The a's will cancel out on both of these, and this one will be multiplied by a factor of 2. So we have 2 times this plus just what was on top here. I've distributed the 2 across, and this is where it starts getting nice. Things start to cancel out. You'll notice that this 2VI/VF is mirrored over here, but it's subtracted. So both of those get canceled out. You'll notice that there is a VI squared over here and 2VI squared, so one of them cancels out. And what we're left with is 2AD is equal to negative VI squared plus VF squared. Not done yet. We're just going to rearrange this into the same way that the reference table has it, and that is VF squared is equal to VI squared plus 2AD. All I did was add both sides. So lots of stuff happened there with mathematically, but the point of this again was just to show we started with two equations where we knew where they came from. We just combined the two and simplified. And what we ended up with is a new equation with different variables. Now we have final velocity, where we did not have before, and actually what we were able to do is get rid of time as well. So if we're missing time from a problem, we don't know how long something happened, we can still solve the problem using this formula. Let's do an example of this. So takeoff speed for a Boeing 747 airplane is about 80 meters per second. It can accelerate at 1.5 meters per second squared. And the Buffalo airport is 2,700 meters. Can a Boeing 747 successfully reach a takeoff speed at Buffalo Airport? Some of you may know the answer to this question. Boeing 747s do not regularly take off at Buffalo Airport. It's generally too big, and it is actually a pretty close answer we get here. But there is one that has, and that is Air Force One. So a couple, at this point, like 8 years ago or so, Air Force One did make a stop at Buffalo Airport. And I distinctly remember it going overhead, and it just seems so unnatural that such a big plane could still fly. So first things first, shopping list. We have the acceleration, 1.5 meters per second squared. We have the distance, the 2,700. We have our initial velocity. If we're reaching takeoff speed, we're starting from rest, and we're speeding up. And my goal here is actually to find the final velocity. Yes, I know the final velocity here is the 80 meters per second. But what I'm going to do is I'm going to find the final velocity and then compare it to the 80. If I get an answer that's bigger than 80, I know it can reach takeoff speed in that amount of distance. If I get something that's less than it, then I know it can't reach takeoff speed. So let's see if it's only Air Force One that can do it, if it's probably souped up special engines, or if it's any plane in general. So I'm going to take my equation, and I'm going to plug in all of the numbers. Now, what you'll notice here, something very important is missing from this, and that is the units. Always, always, always include units. And just like before, because there's units, make sure that you put parentheses around so you don't lose the squared in the units. And when you plug this directly into your calculator, you get VF squared is equal to 8,100 and meters squared per second squared. Take the square root of both sides, and we get 90 meters per second. So it is indeed fast enough to reach takeoff speed. It just doesn't happen very often. Now, the number one problem that we're going to have, and I mentioned this before, is picking the right equation. The challenge in a physics problem is not the math, or it shouldn't be at least. The challenge in the physics problem is picking the right equation, the right relationship for a given situation. So when we're looking between our two new equations, the VF squared formula and L Grande, the big difference that I look for in a problem is time. If time is not in the problem, if it's not given to you, or you're not asked to figure it out, then I would say that this is that the equation you should use is the VF squared formula. If time is in the problem, we should be using the distance formula. Now, keep in mind that we have one other formula under our belt, and that is the VF is equal to VI plus AT. The difference between that and the other two is you'll notice it's missing distance. So if the problem doesn't involve distance whatsoever, then that's the appropriate equation. With these equations, we can solve for any problem with one-dimensional motion. and two-dimensional motion too. So using these equations is key. It's just picking the correct one for the situation is what the challenge is. And the final questions in our Edpuzzle for today will be simply looking at a question, and then I'm going to ask you to pick the right equation. Not even do the math, just figure out what is the equation that you should use in that situation. And that's all we're going to do. Because I trust that even if you can't do the math now, with practice you will be able to. But what you really need practice with is picking the correct equation, because that's going to be a skill we need throughout the entire year as we get more and more equations under our belt, is figuring out what one is important for which situation. That's all I have for you today. I hope you have a good one.